So as a summary of the section, you can see that it's always going to be a toggle between chemical potential energy and electrical potential energy. And if we've got chemical potential energy stored in bonds and we connect that up in a useful way, we can allow electrical potential energy to flow in the form of electrons through the external circuit, and that would then be a spontaneous reaction. Your E naught cell value, whichever equation you use, would return a positive value. However, if you have to provide electrical energy in order to get a chemical reaction to occur, that would obviously be non-spontaneous because we're providing energy, and your E naught cell value will be negative, and that would be an example of an electrolytic cell. Electricity, lytic, linked to lysis, linked to splitting, so using electricity to split chemical bonds, basically. So using the SEP table, and just to look for trends on the SEP table, remember, you don't need to learn anything off by heart, you just need to know how to read it. So if, for example, we've got some substances that have been linked together in a chemical reaction, maybe we've got this substance, which would obviously undergo oxidation, and these two substances which would undergo reduction. Now, this reducing agent being near to the top, a strong reducing agent, according to our table, therefore it would undergo oxidation quite easily. These two, also both strong oxidizing agents, would undergo reduction quite easily, but which one would occur preferentially, you need to then look at your table. So obviously the only reducing agent is on this side, so it's definitely going to take part in the reaction. Between these two, although they are both strong, the one that will preferentially be reduced is the one that is closest to the bottom because of it being a stronger oxidizing agent. And then if using the tick method, you would say that this then forms a tick between the two, and so that would then be a spontaneous reaction. And what we then notice between these two is that it's going to return the largest EMF that can be produced, possibly. So it's the two that are technically furthest apart if you're looking at a galvanic cell. If you're looking at an electrolytic cell, though, say we've got maybe a substance on this side that would then be reduced, and maybe we've got two substances over here that would be oxidized. So between them, if we use our table technique, the only oxidizing agent is this one, so that has to take part. Between these two, they are both pretty weak reducing agents, but the one that is closest to the top, the one that is less weak, is going to be this one. So although they are going to be non-spontaneous, and we can't draw a tick between them, it's like a cross instead, so it's not spontaneous, but it ends up being the two that are closest together. So please don't learn anything off by heart in terms of two that are furthest apart or closest together. Just use your table, just use the arrows, and the right answer will pop out. What you notice about these ones is that it returns the one, because it's that are closest together, it returns the one with the smallest EMF required, which is quite logical. It's saying if we are getting energy out, we want the largest possible output. If we are having to provide energy, we want to provide the least amount of energy. And I had a boy a good couple of years ago who had a great analogy for this. He said, if you go to a restaurant and somebody else is paying, then you order the most expensive thing on the menu. If you go to the restaurant and you're paying, then you order the cheapest thing on the menu, which is quite a fun way of remembering it.